Folks, we'll get started in just a second here. A couple people have joined the class that weren't here on Monday. If that is you, I forgot to bring up some additional copies of the syllabus, so I'll get them for you afterwards. Follow me down to my office and I'll get them for you. We have our first lab together tomorrow. I will mention this again towards the end of the lecture, but if I don't have a chance to get through it since I'm already behind in all my classes so far, make sure you bring a calculator with you. We'll need it tomorrow, okay? Scientific calculator. We're going to be doing some number crunching. Not particularly difficult stuff, but stuff I want you to be familiar with a little bit in terms of geophysics, all right? We had our first introductory lecture, and it was basically just going over policy, etc. We'll talk more about some of the other components of the course as we get through it, including the format of the exams, which I haven't even had a chance to think about yet, so I'm not really prepared to talk about that at this point, all right? Today we're going to carry on with wave theory, and some of the stuff we're going to be talking about today is essentially the numbers behind the way refraction works as is applied to seismology. It's not all that much stuff you have to worry about in this class because I really don't push the whole numbers thing, but you do have to have an understanding that everything we're going to be talking about is going to be regulated by the physics involved in things, because after all, this is a geophysics class, okay? Have a seat and enjoy yourself, and we'll get started. Is it warm in here, or is it just me? Feels humid. You know, there was fog this morning. Can you believe that? Fog? I mean, this is one of the foggiest places in the world, I suppose, but it's been so dry lately. I mean, nothing is growing. I had some kids come up to my house the other day and say, like, would you like us to cut your grass? And I looked at it. There's no grass. It's like moving the dirt around a little bit. So, wettest city in the United States, my ass. Anyway, today this is lecture number 2. We're talking about wave theory part 2. I didn't get through entirely everything I wanted to before, so we have some stuff to get caught up on, which you'll see in just a second here. All right, last time we met, reminder, we had introductions, class policy, etc. A reminder, every time there's a transition in terms of instructors, you've got to learn new tricks, new lecture styles and techniques, etc. So you just have to play catch up a little bit. We had our first introduction to geophysics, at least from my point of view, what I'm going to be doing, and then we started wave theory in terms of properties of rocks. A reminder of what we kind of talked about last time. We do geophysical analysis not because we particularly want to all the time. I think most geologists would argue that it's always better to get access to the rocks, but that isn't always practical or realistic. So you do geophysical analysis when you have no direct access to the rocks, a lot of subsurface stuff, for example. You want to model an area very largely, and in some cases cheaply, and remember this if you know what you're looking for, okay? So you can actually target certain techniques if there is some sort of information that you can take to help you to model things, or at least to establish some sort of a geophysical technique. And that doesn't really make a lot of sense, but I think you know where I'm going with it. The main thing to note, though, is that geophysics is only an approximation of what the rocks are below the surface. 2 scales of geophysical analysis. We have the small scale, the single well type side of things. And again, this is from my point of view, dealing primarily with the petroleum industry side of things. Small scale is a single well, whereas large scale is a basin-wide survey. And these are the ones that are particularly useful. And this is where we're going to spend a lot of our time in the labs a little bit later on, is talking about modeling large areas, coming up with the idea of what the layout of the geology is by using either electric well logs or by using seismic survey lines. And then we talked about the different types of geophysics that are out there, and there's a lot. I mean, there's a listing of some of the major ones. Connors has already gone over at least half of those. I'll take care of the other half. And the difference between passive and active. Again, passive is where you just basically go out there and listen to things. Active is when you actually are starting to provide a signal and interpreting how the signal works through there. And then we got into wave theory, okay? And we started off by basically saying is that there's some assumptions you have to make when you're dealing with geophysical analysis. While the rock layers themselves are different, we have to assume that they're largely homogeneous in terms of understanding how the waves travel through them. All right, now that is incorrect overall, and in some cases you look for those kind of non-homogeneous components to look for something of value within the rocks, for example, petroleum and natural gas. But at this point anyway, when we're doing the interpretation of the way waves travel through rocks, we have to have some assumptions, and this is one of the ones we do. We also talk about elastic behavior of the waves, okay, and how the media itself is going to behave elastically, except in the vicinity of where you actually induce the component or the wave that you're applying to the rock. there you end up getting permanent deformation. Okay, but for the most part, once you get away from this impact point, then we deal with the whole idea of the waves traveling through the rocks in elastic fashion. All right, now that was then. Here's what we're going to be doing today. We're going to be focusing primarily on refraction, reflection. We have to go over a little bit of stuff that I didn't get a chance to talk about previously. So we'll finish off the whole wave theory component of things. Then we'll talk about wavefront mechanics, wave propagation, wave reflection, and Snell's law. Snell's law is something that is most often applied to optical properties. But after a while, you're going to realize that whether you're talking about seismic waves or light waves, the dynamics of how waves travel through materials are the same. It's just that the substances are different and the frequencies in which they're traveling through are different. So Snell's law works for understanding how waves behave through rocks in the same way as it deals with how light waves travel through minerals and substances. All right, so wave theory continued. I think last time we got as far as talking about this slide, which was an introduction to harmonic motion, at least how harmonic motion is transferred through rock layers. Now in this image, what you're looking at is essentially a shot point as illustrated by the point P in the center of the concentric circles. It's at this point that the seismic wave enters into the rock body and travels downwards and outwards in a complex series of waves or vibrations. Now the idea that harmonic motion takes place is that these movements travel through the rocks in a uniform fashion. As far as this diagram is concerned, the waves that are identified as surface waves travel along the surface. We'll talk about those in just a few minutes. Those are generally called the surface waves or the L waves. And the waves that travel through the rock, which are illustrated by the bottom part of the spherical layers that you see there, are called the body waves. And those are generally consist of P and S waves, the ones that you're most familiar with from our discussions in Geology 111 in terms of earthquakes, etc. Now, speaking of earthquakes, this next slide shows you what you should already be familiar with in terms of basic seismology. As you should recall from Geology 111, body waves that travel through the earth after an earthquake is generated at a focus on a fault plane can be in one of two fashions. P waves, those are otherwise known as compressive waves, travel through the rocks in the fashion illustrated here, which is in a compressive means. In this case, rocks are pushed together and pulled apart in a compressive fashion, and these waves travel through the rock relatively fast. In fact, P waves travel the fastest of the two types of body waves at approximately 4 kilometers per second or faster. S waves, illustrated by the second part of this diagram, are composed of shear, and in this case the wave movement is in a sliding fashion. And you can see how this motion is different from the P wave motion by looking at the little green square as it gets deformed. The last diagram, which we're going to talk a little bit more about in just a few minutes, are called surface waves. And there's, again, like the body waves of which the P and S waves comprise, surface waves have two components that are basically divided upon in terms of their sense of motion. And again, you'll see that in just a second. These waves travel along the surface, and here you'll see that most of the deformation and the displacement is at the surface, and it diminishes with depth. Now again, these diagrams are particularly useful when you're thinking about the seismology side of geophysics. Yet they also have some importance in terms of what we're going to be doing from the active side of geophysics. Because when we generate a seismic wave that travels through the earth, it is the compressive and shear components that travel through the earth, and it will ultimately reflect and refract from the surfaces that we're interested in. And so we have to have a little bit of an understanding as to how those waves actually work. Now, one last thing before we leave this diagram, if you look at it, and I guess this isn't going to be possible to see in the on the online version of this because you won't be able to see the active GIF. The image is a GIF file, so it actually has movement to it. But you'll see that there's a red dot in the middle of each of the three components, and that red dot will give you an idea of just how the rocks feel movement. So for the P wave, it is a back and forth motion, in this case from the right to the left. The S wave motion has an up and down component to it, and the surface motion is up and down with some lateral displacement as well. Okay, so let's talk now about surface waves. Surface waves travel out along the surface from a seismic event. And again, this is more important if you're dealing with seismology in the sense of studying how earthquakes travel through the earth and the damage associated with, say, a major earthquake. It is the surface waves that largely do most of the damage in an earthquake. Surface waves are generally called L waves, and there are two categories of surface waves that we really need to talk about before we move on any further. And really the only reason we're doing this now is for completeness of your education, because to the best of my knowledge, most geology instructors in Geology 111, while we may talk about surface waves, we don't go into the nitty-gritty about how they actually work. And the next series of diagrams you're going to see are quite nice because they really do illustrate motion associated with seismic waves quite nicely. Here's the first of them. Rayleigh waves, designated by the symbol LR, are waves that vibrate in a vertical orientation. All right, and what this gives you is kind of a forward motion that ultimately will lead to what is known as an ellipsoidal sense of motion. That's the diagram that's illustrated on the bottom of the ellipsoidal diagram you see at the bottom. Now, this diagram shows you what happens to rocks in terms of deformation from the surface down to some unidentified depth here. All right, so what you'll see is the lines that are in the cross-section line will show you how much deformation has taken place. And you'll see that the squares are deformed, stretched out in almost like a funnel-like fashion. If you were to follow a particle that was at the surface, what it would appear to do is go through the motion of that ellipsoid that's on the bottom. Now what you're going to see is the two components, the SV and the P direction. The P is the propagation direction. The SV component is the vertical amount of deformation. You can identify the amount of deformation related to the amount of shock, in other words, the magnitude of the seismic waves that are going through, and also determine the speed in which those rays will propagate. That's what the formula is there at the by the arrow that points the direction of propagation. Now you don't have to worry about what those numbers mean because again we're not really interested in this aspect of things in geology, at least in this course, which is dealing primarily with the applied side of things. But it's important to note that this is one of two components associated with surface waves, the so-called Rayleigh waves. The second component that you have is associated more with almost like a shear component. These are love waves, and love waves are responsible for a distortion where there is a left to right or horizontal displacement as the shock waves come through. Now once again, the diagram you see in the inset shows you what happens to the rocks once they experience love waves. And love waves tend to be the ones that are most destructive at the surface of the earth because they end up moving things back and forth or rocking them. Not particularly a good sense of motion if you're living in a house. Okay? In this case here, you can again determine both the direction and speed of propagation of the love waves once you know a little bit in terms of the magnitude of the earthquake as well as some of the resonance frequencies that are taking place. So in this case, what we got are two types of waves that are associated with seismic activity along the surface, analogous to what you would find with the body waves that occur through after an earthquake, the ones that we were more familiar with, the P and S waves. All right, now, next slide. What we're talking about here now is how the waves actually travel through the rocks, the wave propagation direction. Now, the previous slides that you saw gave you kind of a graphic representation of how the waves travel through rocks. Also gave you the mathematical means by which to determine how fast they go and their propagation direction. But from a purely, I guess, graphic way of illustrating how these waves travel through the rocks, it's better to consider the motion of each of the so-called wave fronts. Now, wave front is essentially where you end up having the motion of all the particles vibrating the same. And in this case, what you end up getting is, at least at the start, is what's called a spherical wavefront. Now, to envision what this is involving, imagine again that you have some sort of a shot point at P in the middle of the circular diagram in the inset. This is where you administer the shock, or if you're still thinking about earthquakes, this is where the earthquake foci would take place on a fault plane. At this point, seismic waves will radiate in all directions. Those that radiate along the surface waves, travel horizontally along the surface, but the body waves, the P and S components, will travel in concentric shells into the interior of the Earth. Initially, the wavefront starts off as being spherical in nature, and that's the important thing to consider. However, very quickly, what will happen is, as you travel away from the shot point or the focus of an earthquake, at speeds often in excess of 4 kilometers per second, the wavefront starts to flatten out. Eventually, it approaches what we'd almost call a plane wave. And a plane wave is something that more or less is moving along as a sheet of paper or a sail would on a sailboat at sea. Now, the dynamics are still the same here as they would be for the waves that start off as being spherical. There is a propagation direction. Okay, this is the direction that the seismic wave is traveling along. There's also going to be vibration directions, depending upon what the nature of the wave is and how the particles are moving along the wavefront. There is the horizontal component, here designated as SH. There's also the vertical component, here designated by SV. So this is the deformation that is taking place along the rocks. Now remember again, we're talking harmonic elastic motion. And that's important to note because that means that there's no permanent deformation as these shock waves are traveling through the rocks. Now we can model it, we can mathematically do things, and I don't want anybody to start panicking by looking at the formulas here because this is not something I do in this part of the course. If you were to be doing a graduate level course on geophysics, you may be expected to start modeling how fast these waves would actually travel. And if you wanted to, here is a I was going to say a fairly simple equation, but obviously differential equations like this are not simple. But it is possible to model how fast the waves will travel through the rocks. More importantly, it's also possible to calculate various components of rock dynamics if you know how fast the waves actually did travel through the rocks. And for those of you that are sitting back thinking like, well why do we even care about this? Again, you have to realize that this is the type of stuff that was done in order to model what the interior of the Earth was like. Remember, we know an awful lot about the interior of the Earth, at least we think we do. We know about potential densities of the rocks. We know about their states, whether they're liquids or solids, whether they're rigid, whether they're ductile, in part because we determined how fast it took the waves to travel through those rocks. And from knowing some basic things, it allowed us to determine that there are certain properties of the rocks, including their densities, which we can measure remotely. So mathematics like this does play an important role in terms of our ability to interpret what the nature of the rocks are below the surface. And as I said, this might be the type of thing that if you were working as a geophysicist studying deep earth mechanics of rocks, you might have to actually start worrying about. But in this class, it's not something you really have to be concerned about. That being said, it's also important to tell you that there's other mathematical relationships. This one is called the one-dimensional wave equation. And you can go on and on and on. This particular slide I just put in here now because well, I don't know why I put this in here. I guess I put it in here to prove to you that math is important in geology, even if your humble instructor is not going to be talking about this, in part because I haven't got a clue as to what this all means. But it does allow us, again, to accept that if you wanted to get into the mechanics behind how waves work, if you wanted to get into the ideas of how rocks and rock behavior controls wave dynamics, then you could certainly go ahead and do it. And this is the three-dimensional wave modeling curve that you can use. Okay, so if you want to, you can play this game. And for those of you that are inclined to mathematics, I encourage, and seriously, because if you have any love for mathematics, if it's something that if it is a discipline that you can handle without cringing, then there's an awful lot of opportunities available to you. Because as a general rule, most people that are geologists get into geology in part because they can get away from the mathematics. So if you have an understanding of mathematics and are also interested in geology, there's an awful lot of stuff that you'd be capable of doing in the real world. So Fortunately, and for the rest of you, which includes myself, for those of you that are math phobes or don't really like the whole idea of physics in general, big deal, you don't need to worry about it. If you end up working as a petroleum geologist, if you're a geophysicist and hired on to determine where possible sites are for petroleum, then you really don't have to worry too much about the mathematics. Although, if you were to work for a company, they would probably send you off for a number of courses, short courses, to learn more about things. And I got to tell you, okay, if you ever have the opportunity to go to do a short course, choose the short courses that are going to be the most challenging for you. Everybody does the easy stuff, but few people will actually push themselves as far as they should when they get into a professional situation. So always take an opportunity to learn stuff you don't already know, and that goes to the mathematics. Now, I said that for most of us we don't have to worry about the mathematics, and this is true because you don't need an awful lot of mathematics to look at a diagram like this and interpret the structures that you see here. Because ultimately, remember, if you work for an oil company, the oil company is going to hire you because what they want is for you to find them money. Well, maybe not money, but you know what I mean. They want you to find them oil and gas, something that will make money for them. And that requires you to be able to interpret seismic lines like this one and be able to show where the faults are, where the structures are, and ultimately try to determine the best place to look for resources like oil, natural gas, and in some cases water. And this is not going to come easy. Nothing worthwhile doing ever comes easy. You always have to work at it. You need practice, and you need as much practice as you possibly get. And trust me on this, because right now I'm taking a ceramics course, and I'm learning how to throw bowls on a wheel, and boy, it is not easy. What you think is so simple, just taking a wad of clay, spinning it around, and turning it into something that's cylindrical, is a lot more challenging than that would ever appear until you actually start trying to do it. And the only way I'm going to get any better at it is if I keep practicing, as you are going to have to do if you're going to succeed in geophysics, or if you're going to succeed in geology or anything at all. Okay, so practice, 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 practice. Now with that, let's turn away from the basic mathematics of things now and start talking a little bit more about physics and how waves actually propagate through media. Now, the first thing we're going to start talking about is waves or wave behavior based upon our understanding of optics. And you have to understand that this was done a lot earlier in the past, certainly, than our understanding of how seismic waves travel through rocks. But waves, in many ways, are consistent in their behavior. So it doesn't matter if you're actually thinking about sound waves, light waves, or seismic waves. They're all going to follow the same basic rules because they are moving as waveforms. So with that, we can start considering some of the early work that was done about how waves propagate. Let's start off with this character here, Christian Huygens. He was a Dutch mathematician, and back in the late 1600s, he started experimenting with or trying to interpret how waves travel from one media to another across what they more or less consider to be an interface. Now, an interface in terms of optics is where you go from one lens to another, or from one media like air to glass. In seismic applications, of course, the interface will be the contact between a shale or a sandstone and a limestone, or a dolomitized limestone and a porous sandstone. All right, so the interface is simply the boundary between successive types of materials. Huygens' principle, and this is a bit of a mouthful here, and you could read this on your own. It's an important consideration because what he managed to do was to determine how basic light, or in this case particle motion, takes place as it's traveling through different media. All right, so this is a pretty cumbersome slide here, so let me highlight certain points of this and then talk you through what it's all about, okay? Now the first part is this, that all points on a wavefront can be regarded as point sources. So if you look, what I've done is I've drawn an arrow from one point to another, and you'll see that from the line AB, where there's a series of 7 points, down to CD, it has been translated through distance of VT, okay? All right, so each one of those points is going to be the source of a propagation of what are called spherical waves. And you can more or less see the part of the wave associated with that one point. Let me advance to the next slide to show you and highlight it for you, okay? So there it is. So that is a spherical point where spherical waves are propagated. Now the reason why it's spherical in nature has to do with the slide that we had a little bit earlier that says that all wavefronts initially propagate as spherical bodies, okay? And notice that each one of those points along the line AB will have a concentric spherical or circular shape associated with it, and each one of them is indicated as a partial circumference that you see there, okay? Now from here, each one of those waves that are generated from each of those points, when you line them all up, they will tangentially arrange to form the next part of the wavefront. All right, so in other words, each one of those points generates a spherical thing, and when you look at where all the spheres come together, it will be part of a wavefront that will travel through rocks, or as Huygens was doing, traveling through through objects that were optically light waves traveling through various optical materials. Okay. Now, taking Huygens' principle and applying it to geology, here is a situation that is going to be very common in any encounter that you do with seismic waves. Okay, so what we have here is a very simple diagram where we have a layer of shale in white with a specific wave velocity and a layer of sandstone in yellow with a different specific velocity. And it's important that you realize that the velocity of the waves traveling through the rocks is going to be controlled by the density of the rocks, and that's going to be important as a controlling influence as to how the waves are going to bend, reflect, and refract through the substances. We're going to come back and talk about that, particularly when we start dealing with terms like acoustic impedance at a later lecture. All right, so here we have shale overlying sandstone, and there is the interface between the two rock types. Now, playing the same game that Huygens did with his optical experimentation, consider this. We have a series of wavefronts impacting the boundary or the interface between the shale and the sandstone as shown here. So at point A, what you will see is that the wavefronts are starting to encounter the interface at different points. All right, and notice, this is important, that each one of those things hits the interface at a different time and a different place relative to each of the previous ones. So again, if you think about each one of those wavefronts generating, again, a spherical wavefront, this time bouncing backwards, because what we're looking at here now is an interface contact which is going to cause wave refraction. So the first one is going to result in a spherical wave traveling back into the body of the rock, as shown here by the small red circle. The next one that hits a little bit later on will generate another wavefront, spherical wavefront, traveling back into the rocks. But by the time it has hit, which is a little bit later than the first one, the first wave has already radiated back into the rock further. And then, of course, the next one that takes place is going to hit a little bit later. By this time, of course, the previous one has expanded a little bit more, and the one that hit first has expanded a little bit more. So what you've got here now is a series of expanding circles, or wavefronts, bouncing back into the shale from the contact with the interface. And like Huygens' principle as he applied it when he was talking about the idea of these wavefronts giving you these tangential contacts, they will do it here too. And what you'll end up getting is this. You will get a reflected wave. There's the wavefront shown in red with an arrow showing you its propagation direction moving back into the rock in the opposite direction to which it first encountered the rock in the first place. Now, not exactly like 180 degrees. There's an angle of reflection here, which we'll talk about in just a second, okay? And this will happen at every point where there is, more or less, a wavefront encountering an interface. Now, if this is starting to look like it's incredibly complex in terms of the amount of waves going to be bouncing off this, you're absolutely correct. Each one of these seismic waves will have waves bouncing back into the rock at different points. So in order to make sense of this, in order to interpret the reflections as well as the waves that are traveling through the rocks a little bit later on, the refractions, requires a pretty powerful computer if you think about it. Now, of course, 50 years ago, this type of stuff required a truck with a almost the equivalent of a supercomputer on the back of it to interpret these things out. Nowadays, a computer that you can buy from Dell off the internet for $500 can have all the mathematical power you need to keep track of all these waves. And the reason for this is simple, because it's mathematically predicted. It is mathematically controlled. Physics is a mathematical subject. Computers, more or less, deal with mathematics. They are perfectly suited by which to record all these different reflections and refractions that are associated with different seismic events. Okay, so that's why you can get away with not understanding really the math behind this, as long as you have the ability to at least interpret the computer interpretations of these different events, and that's what most people do in the geophysical world. All right, so this diagram is right out of actually this is one of the better textbooks that are out there. It's not the one that we kind of offer as a reference book in this course. This is something I have lying around in my office, and it's a real nice little diagram because it more or less takes these principles, puts them in line diagrams. And I mean, if you were to look at this without having me talk you through the previous diagram, it would look hopelessly messy. But by now, I hope you can see that essentially this is the same diagram that I drew for you previously, except that it is drawn a little bit better, a little bit more accurate, etc. on there as well. Okay, so this is the type of thing that the basic textbooks can tell you about how things work. And again, I encourage you, if you ever have a chance to pick up a geophysics book, to pick it up and read it, and not be intimidated by some of the mathematics that it might be included in reference materials like this. Okay. And now while we're at it, here's another diagram, because we alluded to the idea already that there's reflection and refraction. But I've ignored the refraction component of things. This is a companion diagram to the previous one that now has omitted all the reflection components and now is dealing with the refraction side of things. So now we're below the interface, below where the shale and sandstone would be. This is how the wavefronts would travel through the rock below the contact into the sandstone. And again, you can see the concentric circles that generate the tangential wavefront, now designated by the line EB, traveling at a refracted angle through the lower sandstone. So from this one interface, we have reflected waves that are bouncing back towards the surface, and those that are refracted now traveling at a different speed and a different angle through the subsurface. And once again, I want to make sure everyone's clear on this. The reason why we have waves picking up speed and slowing down while they're refracting like this is because seismic waves will travel at different speeds through different materials, controlled primarily by their density and various other components on that. Okay, so for optics, if you remember anything that we did in Geology 302, you know that optics are controlled by the index of refraction, the speed of light through materials. In this case, we're talking about simply the acoustic impedance, the speed of waves through rock bodies, etc. Now, if you look carefully, pardon me, you're going to start to see some angles in here that should look vaguely familiar to you from your introductory physics courses like Physics 114 or 201. You will see an I and you will see an R, and you should immediately associate those things with the angle of incidence and the angle of refraction. That is us to introduce yet another pretty clever thinker from the 1600s. This time we're going to be talking about Pierre de Fermat. This guy was French. He was a mathematician, and he was one of the important thinkers in terms of optical properties as well. All right, now here's Fermat's principle. Of the many possible paths between 2 points, A and B, the ray, this case being an optical ray, follows the path that gives the shortest travel time between the points. This more or less says that when you have an angle of incidence
identified by I, then it will have a reflected angle that will be equal to the angle of incidence, in this case I prime. All right, now this again is something that you should remember from basic physics classes. And if you don't like this version of it, then you're certainly going to like the following version, because this also has a lot of applications in terms of geology. All right, so there is the diagram again. And this comes from yet another classic book, A First Course in Geophysical Exploration and Interpretation. Here you see the incident ray path indicated by the angle of I, reflected ray path, and then there's the refracted wave path. Okay, and actually that one, there's a little bit of refraction on that, not nearly as much as my liking. The main thing to note here is that this is the basis, or the basic principles behind an important rule, Snell's law, here designated by the relationship sine of the incident ray over the velocity of the incident ray is equal to sine of the refracted ray over the velocity of the refracted wave. This is one of the most important relationships as applied to, of all things, X-ray diffraction. X-ray diffraction is something that is done as a means by which to identify minerals by looking at the spacing of various lattice planes, or the spacing of sheets, if you wish, in micas. Because the spacing between the different sheets can be determined based upon the angles of reflection and refraction between them, you can use Snell's law by which to determine the spacing distance of micas, and through that identify pretty accurately what the micas actually are. And again, if you remember from Geology 302, micas and clay minerals in particular are really difficult things in which to identify in hand specimens. In fact, the only way you can do it realistically is by putting them in the XRD, getting the different spaces of the planes between the different sheets of the clay minerals, and then ultimately determining what they are based upon checking up on known d spaces between the different minerals and all. So Snell's law, as it applies to minerals, is an important thing that we do routinely in crystallography and mineralogy. Now, we don't really call it Snell's law when we're dealing with geophysical interpretations like this. It's better to call it the law of refraction, but it's more or less the same type of thing. And again, it allows you to start determining things like the properties of the rocks that the waves are going through. All right, so important considerations, and nice little crossover thing here between different disciplines in geology as well as with physics, etc. too. Okay. All right. Well, now that we've had a chance to talk a little bit about basic physics of waves, perhaps we should finish off our discussion of wave mechanics. At least general wave mechanics, with the following diagram. This is a reminder that because you are dealing with seismic waves, and seismic waves are the same in terms of basic properties as optical waves or radio waves or sound waves, that means they're going to have measurable amplitudes, measurable frequencies, measurable wave periods, and measurable wave lengths. All right, so these are things that are not all that important with geophysics, certainly not as much as they would be for, say, optical wave mechanics or anything like that, but they are still things that need to be considered periodically when you are actually doing geophysics, especially from modeling seismic waves and interpreting how seismic waves actually work. All right, so summarizing so far what we've done. We've talked a little bit about how waves propagate. We've talked a little bit about how wave fronts move through rocks. We've talked a little bit about the mechanics of waves. We've thrown in Snell law for good measure. I've given you a lot of mathematical relationships that I told you I don't understand and you don't have to worry about here right now. So the next thing to ask is obviously this one. Why should we care? I mean, why are we talking about this at all? I'm talking about it because I think you have to have an understanding that everything we're dealing with in geophysics is modeled and regulated by physical laws. And this is something that a lot of geology doesn't follow. Boy, doesn't that sound terrible? That geology doesn't follow the laws. But you know where I'm going with this. Geology is a non-exact science. If you're studying paleontology, you look at fossils, you get all the fossils you can find out of a rock, and remembering, of course, that
if you get a really fossiliferous limestone, that still might only reflect 0.2% of all the beasties that were alive at the time. So you have to make your best interpretation as to what was going on based upon what was left behind to interpret. All right, so geology is a lot like that. My area of specialization, sedimentology, I'm forever making determinations based upon the best guess I can get out of what's left behind. But when you're dealing with geophysics, following proper geophysical rules, there's a lot of interpretation that has to be made still, but we're following things that now are governed by, well, relationships that are mathematical in nature. So the reason why we should care about understanding, or at least recognizing the importance of mathematics and physics behind this, is that we have to be able to model, interpret, and set up seismic lines that were going to give us the best data based upon our understanding as to how the rocks actually work. So, case in point, this next diagram, which is really messy, I know, is starting to show you what happens as you start having waves travel laterally through rocks. It's giving you an idea now that there's going to be some intervals where there's going to be critical versus supercritical reflections. And this basically is more or less showing you how the waves are going to be bouncing off at different levels. Now, all of these waves are emitted from the same shot point, here indicated by the O position at the surface. They travel through the rocks at different angles and will start bouncing off at different angles as well. In fact, this would allow you to actually find what they refer to here as the critically refracted ray, which follows along the interface. Okay, so here the mathematics, the physics tells us that we're going to have relationships that are going to start passing through the rocks like this. Now, this is going to start causing a lot more, well, let's say interference, although interference probably isn't the right term here, but a lot more reflections are going to be coming off of the rocks that may not be in the best orientation for us. That will generate, in some cases, a lot of noise. Now, why this is important is that if you are going to be responsible for planning a seismic line, then you've got to be able to determine where is the best position to mount your geophones and also to position your shot points. The diagram you're looking at here now shows you two possible configurations for establishing a geophysical line between various shot points. All right, so the one that's on the right, sorry, the one that's on the left, this is the 24 group split spread, all right, has got your shot points that are split in two, where you have your geophones, which are indicated by the dots between the shot points, split into two components, where 3 shot points more or less occur on either side and in the middle of those. The 24 group off end split has 2 shot points with the 24 geophones more or less aligned up between them. Now, which type of setup you choose would be dependent upon the type of information that you're trying to concentrate on. I am not qualified to determine or to talk about what's the best opportunity here. In fact, most geologists would never have to actually have a say in how this would be set up, because again, we're the ones that are interpreting the data, not trying to come up with the actual data in the first place. Although some of you might get involved with say some of the support industry, working for Schlumberger, Dresser Atlas, or some of the other major support groups that are out there, in which case you might have a hand in setting up the shot points. So understanding the math here and what you're actually looking for is going to be very, very important. Here's another diagram that shows you again another set of shot points with geophones and groups of geophones between different points. And again, I throw this in here now just to more or less point out that understanding the math allows you to better understand how to get the data you actually need. Because eventually you're going to see that there are going to be situations where you're going to have a good seismic line and one that is a bad seismic line. One that's got a lot of noise in it where you can't make heads or tails out of it. I personally have actually had to deal with interpreting bad seismic lines, and I'll tell you there's no joy in it, because if you're not certain what you're doing, then you could be costing an oil company an awful lot of money. So again, it's
it's important that you understand that the orientation of things, the types of rocks you're looking for, are going to, in some way at least, control how you go about actually planning your geophysical surveys. And this last diagram, before we break for today, also indicates that if you start having inclined strata, and below the subsurface, depending how far you go down, this is almost going to be the norm, that here the reflections are going to be, again, different. And it becomes very difficult to come up with the perfect, I was going to say the perfect shot orientation, the perfect geophone spacing, that's going to give you really good surfaces or reflections for rocks that might be variably oriented below the surface. Sometimes you get strong reflections, sometimes you don't get so strong reflections. And ultimately, what you want to have is a very good seismic line where any variation that you see in the intensity of reflections is controlled not by things like the orientation of reflected angles, but by the rock properties themselves. That's the difference between a good seismic line and one that is pretty wonky and useless. All right, now with that, we'll call it quits for today. Thursday's lab, which is tomorrow, will be dealing with mathematics. It's not going to be a particularly difficult lab, but it's going to allow you to start calculating some important variables that will be necessary in any interpretation of geophysical applied geophysics in the oil companies, etc. So please bring a scientific calculator, one that can do just basic calculations, to lab tomorrow. It's not a long exercise, something you can do at home, and I'll talk you through how to do it. And next week, Monday, I'm not going to be back in time to give you your lecture. I have to do something out of town, and I will get back at around 11 o'clock or so. My flight arrives at 11 o'clock anyway. And by the time we get back to the university, it's not going to be time for you guys, obviously. So I will leave a lecture for you online. Check the web page. If I'm not mistaken, I heard rumors that the web page was going to be accessible a little bit later on today. I will check that the first opportunity I have. The minute it is, I will upload your webpage, start putting these lectures on there, and that's where your information station will be for the course. Okay, so tomorrow we'll see you in lab, and next Monday I will not see you, but there will be a lecture for you. And a reminder, folks, okay, I want to make sure you guys are watching that lecture, so you can expect to have a kind of a short quiz or something that will count for a few points anyway towards your grade in this class, and it will be based upon that online lecture. So no stuffing around and ignoring it until the last minute. Make sure you watch that lecture as soon as you can, because you're going to get tested on it on Wednesday. Anyway, with that, I will say goodbye, and I'll see you in lab tomorrow.